In this lecture, we are going to introduce the concept of a spin. So, you would have studied about the Stern-Glass experiment, wherein if you send a beam of electrons, right? If you send a beam of electrons and you send them in a magnetic field, okay, if you send them in a magnetic field, one part gets deflected upward and one part gets deflected downward. Okay, so now to understand this, to explain this, the spin property was introduced, right? So the electron behaves. So the phenomena here is nothing but the a charged particle moving in a magnetic field experiences a force. But why is one force acting upward? Why is one force acting downward? So this, to explain this, the property of spin was introduced. So we already studied about the angular momentum, right? So the angular momentum, right? So the angular momentum is like, if this is the nucleus and if the electron was going about in orbit, right? If the electron was going about in orbit, it has some angular momentum, right? It has some angular momentum. Now, if the electron here, a point particle only electron is, right? We consider it as a point particle, but let's say it was spinning about its own axis. Okay, it is spinning about its own axis. Okay, if one electron is spinning in the clockwise direction and another electron is spinning in the anti-clockwise direction. Okay, my direction, right. Yeah, one electron is spinning in the clockwise, let's take one electron is, so it's spinning about its own axis also. So this is why some electrons we consider to be spinning in the clockwise direction and some electrons in the anti-clockwise direction. So because of these opposite spins, right, that is why these one particle gets reflected upward and one particle gets reflected in the opposite direction, because they have opposite spins, right? Opposite spins. So the theory for spin will be just like the angular momentum theory, because where the phenomena, the physical phenomena is the same, right? Here it is revolution, that is rotation. Okay, so the theory is just the carbon copy. So we studied about the angular momentum operators. So the same, you just replace the L in the place, so you just replace the L by Sx. Okay, so similarly you replace Sy, the Ly operator, by Sy, and so similarly you replace the other operators correspondingly, you will get the spin theory. Okay, you get the spin theory. So I'll explain what this means, each one means physically. So this is the commutation relations between the operators, and this is the we had defined the raising and the lowering operator. So it raises the spin state by 1, it lowers, the plus raises the spin state by 1, the eigenvalue m goes up by 1, and the minus decreases the eigenvalue by 1. The m value in the quantum number m, right, that decreases by 1. So this is the raising and the lowering operator, and the and we know that the spin progresses as half integer values. Okay, so the values s can take here as increases by half integer, so 0, half, 1, 3/2, and m value can go from minus s to plus s. So and it is incremented by 1. Okay, minus s to plus s, and each value is incremented by 1. So now let us work out the spin theory for halves integer, where for s is equal to half. Now this is important because electron has a spin half. Okay, electron has a spin half. The clockwise spin will be plus half. The anti-clockwise spin will be minus half. Okay, so we're going to work out the spin theory for the spin half particles, and similarly you can do it for others. So what we do is we take the spinor. Okay, so the wave function, electron wave function, composed of the spatial part, which you get by the solving the Schrodinger equation psi, right? Get by solving the Schrodinger equation psi. And then the spin part, okay, the spin part is the spinor component, okay, the spinor component, okay, so spinor component, okay. So now, so that is what this is. So now we're going to work out this spinor component. It's called a spinor. Now we're going to take uh, two bases. Okay, so two bases refers to, one refers to spin up state. So that is the eigenstate spin up state. Okay, and another refers to the spin down state. Okay, so spin up is we can take to be clockwise, spin down to be anti-clockwise. Okay, and using these basis vectors, okay, so we can span the entire system. That means, so if you have a, so you can see that written out here. This is the spin up state. This is the spin down state. Okay, this is spin up, this is spin down. Now these are the spin up and spin down is taken in linear combination. That is because you have a scalar here A and you have a scalar here B. Okay, so it's just like you take some vectors in linear combination, right? So if you want to represent uh, in a two-dimensional vector, okay, like R vector, okay, you if you have the basis vectors I and J, okay, you can represent any vector by taking linear combinations of these vectors, right? So you can represent any vectors. You can take 3i. You can represent any vector by taking linear combinations of these basis vectors. So this I and j is the basis vector, right? So similarly, here we have this chi plus and chi minus as the basis vectors. Okay, so that is the basis vectors. Now we have to work out what this spinor will be. Okay, so we'll get that by following some like we had studied the operator relations, right? So we had studied that if you operate a square, right, on uh, on a eigen function, you get h square s plus 1 times the eigen function. So this is a, if you substitute the spinor in this eigenvalue equation, okay, this is some sort of an eigenvalue equation. So this operator operates on this function, gives this result, okay, gives this result times the function itself. So similarly we work out these eigenvalue equations, these operator relations in every case, and using this what we can do is we can solve for the operators, the value of the operators, because we know the value of the we know what happened, we know psi plus, okay, we know the eigenvalues. So once you write out these equations explicitly, you can solve for the s square, s plus and s minus operator. So this operator is nothing but a matrix. Okay, this operator is actually a matrix. So these are operators, s square operator, s plus, s minus. For the case s is equal to half, right? For spin half theory only we're working on these operators. So now this sx, sy and sz operator now can be simplified by introducing the Pauli spin matrices. So this is taken as sigma x. So this whole thing is taken as sigma x. So this becomes simpler. Okay, this some notations here. This is taken as sigma y. This is taken as sigma c. This is spinor Pauli spin matrices. And this would of course be the eigenvectors for sz, because that was the assumption we initially started out with, right? So for this is for s is equal to plus half. Now the h bar is just taken here. This is for s is equal to, so this is for s is equal to plus half case. The h bar is multiplied, is taken here only for a it makes our equations a little simpler. So that is why it's taken like that. So this is for the s is equal to minus half case. Okay, the eigenvalue. Now, yeah, again, the h bar is absorbed into this equation to this eigenvalue just to make some equation simpler. So this was the original assumption itself that we started out with, right? The base vectors 1, 0 and 0, 1. So that will be the eigenvectors or the eigenspinors of SC. Now, what about the eigenspinors of Sx? Because when we solve this, we use this equation, right? SZ. We had used so these equations we wrote out for SZ, and we used these equations only and solved it out, right? For for each case, right? Plus and minus. So what about Sx? Okay, so what about the Sx? Okay, what about Sx? The operator Sx. So for that, what we'll do is, okay, we'll write out the characteristic equation where we'll write out the characteristic equation. So we know this theorem, right? So how do you find the eigenvalues? You find the eigenvalues using this theorem, right? Determinant of the matrix that you want to find the eigenvalues for A minus lambda I is equal to 0, right? Is equal to 0. Now in place of A, you just substitute the matrix Sx, right? What is the matrix Sx? Matrix Sx we wrote out here, right? It is this matrix that we wrote out here. So you just put that and get the characteristic equation and solve for the eigenvalues. So you get the eigenvalues h lambda is equal to plus or minus h bar by 2. Okay. So from the eigenvalues, now you can find the eigenspinors, right? So it's just like solving an eigenvalue problem. Eigenvalues, once you find, you can find the eigenvectors, right? So here in the case these eigenvectors are called eigenspinors. So you find the eigenspinors and you get the eigenspinors for the plus half case, okay, for the h bar by 2, okay, case to be the one given here, and for the h minus h bar by 2 case eigenvalue, you get the eigenvector, the eigenspinor here you get this one, okay, chi minus this is chi plus. And now once you have the basis vectors, right? These eigenspinors are the basis vectors, we said. So the the entire eigenspinor is the linear combination of these two. That was what we said, right? So when we started out, we said you have a some scalar times x x plus chi plus b chi minus. So now we have to apply the normalization condition. The normalization condition sets the value of these this multiplicand factor, okay, before this chi plus to be a plus b divided by square root of 2, and here it sets the normalization condition sets the multiplicative factor to be a minus b divided by square root of 2 for the case chi to be multiplied before chi minus. So here we found out the eigenspinors for Sx case also. So this completes the spin theory. Okay, so the spin theory for particles of S half. S is equal to half.